Okay, so here we have the weird case. So I remember in geometry, there were a whole bunch of postulates and theorems for proving congruency of triangles. So if they had the same matching angle, side, and angle, or angle, angle, side, they would produce the same triangles. They were congruent triangles, or if they had the same sides. But one of them that didn't exist was the SSA postulate. And I remember it because the book was very careful to always write SSA. And that's because if you write it the other way around, ASS, it's a bad word. So there is no ass postulate in geometry. And it turns out the ass situation is where we can get some of the weird triangles. So what I found is a good analogy here is to think of like a crane operator on the ground. You know, he's got his arm extended to whatever length, but that's fixed. He can't change it anymore. And now he's got a certain amount of cable that hangs down from that. What we're trying to know is, does he have enough cable to even reach the ground? Does he just barely reach the ground? Does he have enough that there's multiple places it could go to be pulled taut? Or is A so long that the only way it could go is if it went further out? So we have up at the top where they describe these, but they define this side H, or rather don't define it. So H here is if we have the perfect right triangle. Then the sine of alpha would be A over B. Where just beta happened to be the potential right angle. And so that height then is B times the sine of alpha. We could also use the law of sines to set that up because the sine of 90 degrees is 1. So that part of it would disappear and we would still end up with the same thing. So if, whenever we're looking at one of these weird ass situations, one of the things we're going to want to check is the length of the arm of the crane times the sine of the angle, and see if our third side is that length at least. And then we can kind of reason through, okay, is it going to be which of these four situations? And a lot of this has to do with A in relation to B. So if A is smaller than B, then we have our potential double thing, but it also has to be bigger than H. So there's enough give in the line to be able to run it one way or the other. And then for this one, if A equals B, if I tried to run it the other way, I would be running back along the crane itself, and that doesn't make a triangle. That just makes a line segment. So that's why the equal B is put in this case, but it makes a fully open triangle. All right. So we talked about the weird situations. So now we're actually going to work on a triangle. So it says oblique triangles. Just so you know, oblique triangles are triangles that are not necessarily right triangles. I say not necessarily because like we see the special case of a right triangle here, but generally when we say something is oblique, for sure it means don't assume anything is 90 degrees. If it happens something ends up being 90 degrees, okay, cool, but don't assume it. All right, so we have this triangle set up here. And they ask for the missing side and missing angle measures to the nearest tenth. All right. So my missing side here, all we have is law of sines right now. So To get this missing side, I also need the missing angle. In order to get the missing angle, I need to know 2 of the 3 angles. So my first thing is actually going to be to solve for beta. So the sine of alpha over A equals the sine of beta over B. So this is the sine of 35 degrees over 6 equals the sine of beta over B is 8. All right, so my goal is to get beta by itself. So I have a sine, that is not multiplication, that is taking the sine of beta. So we would say sine is applied to beta, or we're doing sine of beta, not sine times beta. So first thing there is we need to cancel out the 8 before we can deal with the sine. So I'm going to multiply both sides by 8. I could reduce this, but I'm not going to because we're just going to be putting this in the calculator. So the sine of 35 degrees over 6. So we need to make sure our calculator is in degrees. And I'm actually going to move so we have the sine of beta over here. Now, I prefer doing all of my equation solving steps, so I have one thing to type in the calculator. It'll be a crazy looking thing, but that way I'm rounding as little as possible. It's also, if you're going to have to like program formulas in on a computer, you need to be able to manipulate all of the variables, like know where they go. Even if you have them defined, they're going to be defined in the program, not a fixed constant. So you're still going to have to put those names in spaces. So it is actually really useful to be able to manipulate equations, whether they're all variables or all numbers. Now, to get beta by itself, this is where I would take the inverse sine. Of both sides. So we pull out the handy dandy calculator. Okay, so shift sine inverse of 8 times the sine of 35 degrees divided by 6. Now, like notice those blue parentheses? I need to make sure everything in the parentheses is inside the sine function. So my calculator does a sine instead of sine -1. And that is what I typed. And it tells me $49.8864, blah, blah, blah. What did they say? Round to the nearest 10th. All right, so our beta is going to be 49.9 degrees. So now that I know both alpha and beta, I need gamma. So all 3 angles in a triangle add to 180 degrees. So I have 35 plus 49.9 plus gamma equals 180. So this is 84.8864 plus gamma equals 180. So we're going to do 180 minus this. So gamma is 95.11359 degrees. So 95.1 degrees. Now we have that third angle. Now we can finally find that missing side length. Now I will say though, like when you look at the 49.9, that angle is actually acute. So what we're really finding here is a triangle that looks like this. The alternate case where it actually looks like it does in the picture, we have to consider the supplementary angle. So when I look at that weird, could be one or the other situation here, I just figured out this angle, and because this is an isosceles triangle, those sides are equal. The angles opposite them must be equal. So then this angle that I actually want to know here is whatever it takes to add to 180 with the angle I just found. So that's how we get our second triangle and angle measures. All right, so we had 49.9. So when this is an oblique triangle, this is 180 minus 49.9. And we get, this is 130.1, and that plus 35, subtracted off of 180, is 14.9. So I know these are crazy when there is the possibility of two things. So in my first case, I still need to figure out side C. So I would have the sine of 95.1 over C equals the sine of 35 over 6. So multiply both sides by 6C, or just 6. Divide by this other stuff. Basically, when you have this kind of fraction equals fraction setup, you can trade stuff across or just multiply by the common denominator. So I have 6 times the sine of 951 equals C times the sine of 35. And then we divide both sides by the sine of 35. Okay, so 6 times the sine 95.1 divided by the sine of 35. All right, so all that for case 1. Case 2, I figured out case 2 from case 1. And what this is banking on is that the sine of an angle larger than 90 degrees of an obtuse angle is the same as the sine of the supplementary angle. Okay, no, that was the previous problem. All right. So now we are just going to use our Pythagorean, the law of sines. So the sine of 14.9 over c equals the sine of 35 degrees over 6. My common denominator would be 6 times c. So I have 6 sine of 14.9 equals the c times sine of 35. 6 sine of 14.9 divided by the sine of 35. 6 sine 14.9 divided by the sine of 35. All right, and then rounded, we get 2.7. So I just want to go back to our picture. 2.7 is now our smallest side. The angle opposite that is the smallest angle. So that makes sense with our small to small, big to big reasoning. The angle opposite the 8, the 130.1, well bigger than the 35. So that is how the ambiguous case can work. Sometimes instead your answer is just no answer. There's no solution. But part of this is like knowing that and seeing what your calculator gives you. All right, I'm going to cut it here and then record another.